Many people believe that the age of dinosaurs is a time of the past, but what they don't know is descendants of dinosaurs are still alive today. Believe it or not, the DNA of dinosaurs can be found in the pigeons that prowl the streets of downtown and the chickens that make up our McNuggets. The origin of birds was always an ongoing unsolved mystery, but it wasn't until the discovery of the Archaeopteryx, an animal with both bird and reptilian features, that helped paleontologists unearth the evolutionary story of modern-day birds.
One frozen wasteland later.
In 1861, paleontologist Christian Erich Hallmann von Meyer discovered single fossilized feather similar to modern birds in Bavaria, Germany. The first fossils were found in Solnhofen limestone, famous Langerstätten, which is a site of exceptional fossil preservation that showed clear impression of its characteristic feathers. The fossil was given the name Archaeopteryx, arch meaning ancient and pteryx meaning wings for ancient wing. The Archaeopteryx first appeared 150 million years ago in the Tithonian age of the late Jurassic period. Their habitat consisted of beautiful tree-speckled islands with gymnosperm, such as coniferous trees that are still present in the forests of British Columbia. The climate which the Archaeopteryx thrived in was warm and dry because at that time Germany was situated near the equators. Analysis of the fossil allowed paleontologists to determine that Archaeopteryx had a few particular notable traits. It has sharp-toothed jaws, 3 fingers claws, broad wings, and a long bony tail. It likely weighed about 1.8 to 2 pounds, closely associated with a size of raven. Due to its sharp teeth and the presence of claws, the Archaeopteryx was likely a carnivore that ate small reptiles, amphibian mammals, and insects. From this characteristic, paleontologists initially thought that Archaeopteryx was an ancient bird with reptilian features.
What sets Archaeopteryx apart from reptiles? With their numerous common features such as their full set of teeth, a flat sternum somewhere along here, gastralia, claws, and a long bony tail, there are also many prominent differences. Let's take a look at the pelvis structure. In this video, we can see that the Archaeopteryx walks in an upright position. This is due to an adaptation to the structure of the pelvis, as the femoral head forms a right angle with each step, supporting its movement. Reptiles, on the other hand, are more parallel to the ground and do not have the same range of motion.
Did you know? The shape of the skulls of alligators and birds are comparable to the skull of fossilized dinosaur fetuses. This suggests that birds evolved to look like infantile versions of dinosaurs. Dinosaur embryos go through the process of metamorphosis, which involves the retainment of traits developed during the larval stage into the adult stage.
Following the disproven reptile hypothesis, it was determined that birds evolved from dinosaurs. In dinosaurs, there are 2 types of hip structures that can be seen. In the bird-like hipped ornithischians, the pubis points backwards, whereas in the lizard-like hipped saurischians, the pubis points forward. The Archaeopteryx has a pubis pointing backward. However, it was found to be more related to saurischians, which has the forward-pointing pubis. Paleontologists believe that the difference is because of convergent evolution between the Archaeopteryx and ornithischians, where 2 species developed similar features due to selective pressures of familiar environments or living conditions. The end of the pubis of the Archaeopteryx retained a small hook distinct in saurischians, and the angle between the ilium and the pubis appeared to be intermediate features between dinosaurs and modern birds. Theropods are a diverse group of saurischians which include the T-Rex and velociraptors. Excluding the added wishbone and ischial shape, the skeleton of the Archaeopteryx is nearly identical to that of Coelurosaurus, which is a subgroup under theropods. Furthermore, the Archaeopteryx are theorized to have descended from theropods as their DNA are the most similar. If you look through the geological timescale, there is a gradual acquisition of more bird-like traits such as the wishbone, the smaller claws on the forelimbs, the enlarged sternum, and the general decrease in size. However, in recent years, the traits thought to have categorized Archaeopteryx as bird-like has also been discovered in other theropod fossils. The fossil skeletons of the bird and dinosaur-like organisms such as the Xiaotingya and the Anchiornis were recently discovered in China. Their skeletons were very similar to that of the Archaeopteryx, which challenged its position in the phylogenetic tree. The notable difference between these fossils was the shape of the skull. Xiaotingya and Anchiornis both had a wider jaw and higher skull arch, which was missing in the Archaeopteryx. After further investigation, Xiaotingya and Anchiornis were separated into their own clade Anchiornithidae, as both of them had longitudinal furrows on their phalanx and specific differences which were also observed in their bone and dental structures. This once again set Archaeopteryx as a basal member of the avialic tree. The new phylogenetic tree is this. The avialic clade represents the bird-like dinosaurs that descended from Coelurosaurs and are currently their living representatives are modern birds.
What led scientists to believe that the Archaeopteryx was a bird were its undeniable feathers, wings, and reduced fingers. Additionally, the Archaeopteryx had a furcula, otherwise known as a wishbone, which strengthens the skeleton to withstand flight, similar in modern birds. Furthermore, it had a large sternum, implying it had muscles required for some form of flight. The primitive shoulder girdle and the cartilage breastbones were also a point of interest as it hinted at limited flying ability. This feature is similar to what is found in modern-day pheasants, meaning they likely flew short distances for hunting, escaping, or climbing trees.
In 1996, over a century after Archaeopteryx was identified, the fossil of Sinosauropteryx was discovered. Sinosauropteryx was a non-avian dinosaur with protofeathers. Protofeathers are the precursor of modern-day bird feathers. The Sinosauropteryx caused paleontologists to reconsider their findings and come to the conclusion that feathers were not actually a trait exclusive to birds and flight, but instead a trait that birds adopted from their dinosaur ancestors. From this, paleontologists believed Archaeopteryx was not actually a bird, but a bird-like dinosaur that represented the transitions of dinosaur to bird. Then comes the question, what were the purpose of feathers for dinosaurs, especially the ones that couldn't even fly? Well, we can actually look to modern-day birds for hints. For instance, plumage for thermoregulation, seen mainly in flightless birds, colorful mating displays, and finally the ability to fly are all functions of these protofeathers. These inferences show how the features of modern birds can give us amazing insights on the behaviors and purposes of adaptations made by the dinosaurs that have been extinct for over 65 million years.
In addition to this, dinosaurs were once thought to be cold-blooded organisms. However, through research, many researchers are starting to lean towards the idea that the dinosaurs were warm-blooded. This was tested through measuring the growth rings of bones, which shows how fast they develop. The rings produced in the dinosaurs' bones are similar to development of trees, in which it demonstrates the pauses in growth of the dinos. The rings were compared with extinct animals as well as modern animals, and dinosaurs fall right in between. By comparing dinosaurs and recent mammals and birds, this showed that dinosaurs grew quickly like them, which also demonstrates that dinosaurs had similar metabolism like mammals and birds. This hints that dinosaurs could have been endothermic. However, this does not apply for all dinosaurs, since there are many more species that could have not yet been discovered.
What the heck was that sound? Oh, I've attempted to check my phone. Is that coming from the phone? Where is it coming from? Whoa.
Did you know?
With modern-day biogenetic techniques, we can actually figure out the genome of the famous Tyrannosaurus rex. Scientists have actually done this and compared their findings to modern-day animals. The most related living animal to the colossal T-Rex is actually the chicken. This can be seen through other experiments too. Scientists inhibited beak-forming genes within a chicken embryo and saw them develop dinosaur-like faces. Also, when given a long dinosaur-like tail appendage, a chicken begins to walk much like a Tyrannosaurus rex.
And that's the Archaeopteryx, whose fossilized story gave us the insights into the origin of birds and the development of the feathers of flight. While not a true bird like initially thought, it still bridged the gap between modern birds and their dino ancestors. This amazing story, and many others like it, can be found in University of Waterloo's very own Earth Sciences Museum.